All right, welcome ladies and gentlemen. This is video number 6 in our flipped bonding unit. This video is on electronegativity and bond polarity. For this video, you are going to need table S from your reference table, so make sure you have table S open. You're also going to need your notes open to page 41. So page 41 in your notes, table S. Electronegativity and bond polarity. First of all, a review of electronegativity. What does that term mean? How well an atom can attract a shared electron and a bond to itself. How good is an atom at pulling in an electron? Is it really good, in which case its electronegativity is very high, or is it kind of poor, in which case its electronegativity is very low? How well can an atom attract electrons? So we say that very electronegative atoms, they hog the electrons in a bond. They're electron hogs. They pull in the electrons towards themselves. They love those electrons. Now we have these two words, which are very important words in chemistry. Now, before we talk about them with bonding or with molecules, just in general, what does the word polar mean? What does the word nonpolar mean? Polar means different, because if you think about the two poles of the United States, they are on opposite sides. I'm sorry, two poles of the world. They're on two opposite sides of the world. You have the North Pole, you have the South Pole. They're in two totally different locations. One has Santa Claus, the other has penguins. Right? They're different. They're opposite. They are not the same. Someone who is bipolar, right? That means that they have a mental illness and that their brain is kind of operating in two different ways. Sometimes very depressed, sometimes very sort of high anxiety, highly strung. So that's that means different, that means opposite. For us, the big term that we're going to use with polar is asymmetrical, meaning, opposite, not the same. And then nonpolar quite literally just means the opposite of polar, right? So what is the opposite of different? The opposite of different is the same. What's the opposite of uneven? The opposite of uneven is even. And for nonpolar, for us, the term that we're going to use a lot is symmetrical. So we use these words to talk about bonds. A polar covalent bond, first of all, does have to be a covalent bond. So we have electrons being shared. That's important. But how are the electrons being shared? When the electrons are shared unequally, when there's unequal sharing of electrons. Because you can think about it like if I have $100 and I want to share it with you. Technically, if I give you $1, I have shared it with you, but I have not shared it equally. Well, that would be like a polar bond. And the reason that we would have a polar bond, the reason that we would have different unequal sharing of electrons, is if the atoms that are involved in the bond have different electronegativities. Electronegativity is essentially the pull that the atom has on the electron. And if they have different pulls, they're going to share those electrons differently. So the key point here is the greater the difference in electronegativity, which I'll refer to as delta En, right, difference in electronegativity, the more polar the bond. So for example, we have two bonds here, HF and HC. So in order to work out which bond is more polar, what you first start to do is look up electronegativity in table S. And the electronegativity of H is 2.2. And so we have hydrogen in each of those things. The electronegativity of fluorine, though, is 4.0. Fluorine is the most electronegative element on the periodic table. It's awesome at hogging electrons. That's like what it does. No other element quite comes close. And then carbon, the electronegativity of carbon is just 2.6. So difference in electronegativity is literally, you subtract the two numbers, 4.0 minus 2.2, 2.6 minus 2.2. So the the difference in electronegativity in HF is 1.8, right? That's the delta En for HF. Versus the HC bond, that's only 0.4. So we have a much higher difference in electronegativity in HF versus HC, which means that this bond here is much more polar. It's a more polar bond. It's a more different bond. There is greater difference. There is greater asymmetry. It's not nearly as symmetrical as the H to C bond because there's a greater difference in electronegativity. A nonpolar covalent bond, again, we have a sharing of electrons. It has to be covalent, right? Sharing of electrons, covalent, caused by now an equal or nearly equal sharing. And the reason that you'd have equal sharing of electrons is if you have either no difference in electronegativity or a very small difference in electronegativity. So if the electronegativities are very similar between the two atoms, then we're going to have what we call a nonpolar bond, where we have almost equal sharing. And again, as an example, all of our diatomics, right, H2, N2, O2, F2, and then down, right, H and off down, so then also Cl2, Br2, I2? Well, if you consider this bond between two hydrogens, the electronegativity is 2.2 for hydrogen, but then you know also 2.2 for another hydrogen. So subtract 2.2 minus 2.2. What do you get as a delta En? 0. That is non-polar because there's no difference. So they're each equally good at hogging the electron, in this case of hydrogen, they're both kind of bad at hogging the electron, but there's no difference in pull. Another example is O to N. So you look up the electronegativity values. Oxygen is 3.4, nitrogen is 3.0. The delta En value here is 0.4. This is a very small difference. And there's an argument that you can make that it's such a small difference that we're going to basically consider that non-polar, essentially equal. We have a scale for differences in electronegativity, and very small differences in electronegativity we consider nonpolar. When we have sort of medium differences in electronegativity, that's polar covalent. But if the electronegativity difference gets to be really big, then we start saying, hey, that's actually an ionic bond when we have extraordinarily large differences in electronegativity. So with nonpolar covalent, 0.0 to 0.4. If the delta En is 0.0 to 0.4, then we say, you know, that's a small difference, and we're going to call that nonpolar. Polar covalent, 0.4 to 2.0, and I'm sure you're asking, well, you know, how do you categorize it if it's 0.4 exactly? And there's debate there, so really, if it was 0.4 on the button, you could sort of make an argument that it's either, and I wouldn't be too fussy about that with you. So now we have, this is like a medium difference, right? And in this range, that would be considered polar covalence. But again, very large difference in electronegativity, so 2.0 and higher. Again, that's the difference between the two, not what the electronegativity values are, but the difference between the two. That's a very large difference. So we call that ionic bonding. So it's this range. What's the difference in electronegativities? In a polar covalent bond, and one of the things we'll be doing tomorrow is categorizing whether a bond is polar, nonpolar, or ionic based on its differences. In a polar covalent bond, the electrons are held more closely by the atom with a higher electronegativity. So the electrons are actually located a little bit more closer to that more electronegative atom. And what that does, and this is an enormous point, that atom with a higher electronegativity actually has a slight negative side of the bond. Because the electrons are closer to that atom, that side of the bond is actually a little bit negative. I'm not talking about a whole negative charge. I'm not talking like a whole -1, like, whoa, that's too much. I'm talking like a tiny little bit of negative, like a little hint of a negative. Not a whole -1, just a little hint of a negative. So for example, HCl. This is a polar bond because we have a difference in electronegativity that's definitely in the medium area, right? These are our two electronegativity values, 2.2 and 3.2. So our delta En is just about under 1. So that puts it squarely in the polar category. Chlorine is more electronegative. So therefore, chlorine pulls the electrons closer. And we can actually see that here, which hopefully is, you can see a little bit better than the picture in your notes. But this is the chlorine side, and this is the hydrogen side. And you'll notice that there's more electrons by the chlorine, meaning literally the chlorine is pulling the electrons towards it, which gives then this side a slight negative. Now remember, you did see in the comic, that this symbol right here, you saw this symbol as delta negative or delta positive. It means a slight charge. So this chlorine side has this slight negative charge because the electrons are pulled closer to it, which then means that the hydrogen side is left with a slight positive. So the bond is not equal. The bond is different. The bond is asymmetrical. And the electrons are being pulled towards the more electronegative atom. So that means that there are less electrons by the hydrogen. So it's slightly positive. Not a whole positive, just a little bit positive. So just a question, which one holds the electrons closer? We have two bonds here, H to N and C to F. Well, it's all based on electronegativities. So you're looking up in table S, which atom is more electronegative. Nitrogen is more electronegative than hydrogen, which means that nitrogen is going to hold the bonds closer. So the nitrogen side is going to be slight negative or delta negative like that. And then with C to F, again, it's based on electronegativities. Fluorine is more electronegative than carbon, which means that fluorine is going to hold the electrons closer. So I would put it a slight negative next to the F and a slight positive next to the C. And it is possible, just to wrap this up, it is possible to tell if you have a polar bond or a nonpolar bond, essentially just by examining them. Even if you're not given the bond explicitly, like these are all molecules, right? We know that these are molecules, but you can tell that, hopefully you know that in Cl2, that means that you have a Cl to Cl bond, right? And without even looking that up, because they're the same, because they're two of the same elements, that means that we're going to have a nonpolar bond. In H2O, what are the bonds that we have? We have two oxygen to hydrogen bonds. Those two atoms have very different electronegativities. Because they have different electronegativities, that's going to mean that we have a polar bond. In CF4, we have a C to F bond. We have it 4 times. Those two atoms have two different electronegativities, so we know that we have a polar bond. And then Br2, again, if we're just looking at this compound, we know that we have a Br to Br bond. Because those are two of the same atoms, their electronegativities are going to be exactly the same. So the difference in electronegativity is going to be nothing. So we know we are going to have a nonpolar bond. So that's the end of this video. We'll be practicing with polar bonds. And just a bit of a heads up, we also have polar molecules. So that's going to be coming up as well.